hear from Davide Gerosa. Who would like to introduce him? Paul, would you like?
I think we've already had him introduced. So David is going to talking to us today about growing up, the next generation of black holes moving out of the cluster. Go ahead and take it away.
And I just wanted to remind everyone that you can raise your hand if you go to the participants button. You just click on participants, and then you will see a menu of options, one of which is raise hand on the bottom left. If you click on that, then the speaker will know that you want to ask a question, so you can interrupt in the middle.
And one other thing too, if you have your audio or video on right now, please mute and turn the video off. Thanks.
So I don't see the hands because I have my slides full screen. So if somebody raises a hand, please, if somebody else can moderate and let me know.
Oh, wait, do you see in the bottom of your screen participants?
Yeah, but the thing is that in order for you to see the slides full screen.
No, that's okay. You can still see, you can still, oh, I see. For us not to see ourselves, you're saying?
Yeah. Otherwise you would see, yeah, you know, my desktop and things.
Okay.
Oh no, wait, maybe. Oh no, wait. Okay. No, I think I did. I have a tab with the participants. All right. Well, thanks a lot for originally for inviting me to Cambridge. I'm sorry I cannot be there. I hope I can come visit. You know, soon at some point where we're back. You know, going out. So what I want to present today is based on this work. You know, you see the archive reference there, completed with Emanuele Berti from Johns Hopkins, about understanding if and how detection of gravitational waves from globular clusters or in general closed environment can provide, what kind of constraints they can provide on these kind of environments they live in. So here is a brief outline of my talk. So I'll first, you know, give a, you know, brief overview of where we stand in gravitational wave astronomy, and then move on to why the occurrence of multiple generations of black holes could be promising and perhaps even hinted in one of the observed events. Point 3 is going to be why the escape speed of the environments where these black holes live is a crucial parameter of this whole business and can actually be constrained. And then I'll conclude with some, you know, thoughts on what could be the right environment to produce these kind of these specific events. All right. So here, what I have is the latest, you know, cumulative samples of all the black holes, of all the gravitational wave events, downloaded from the LIGO, you know, Twitter feed or so yesterday. Unfortunately, I'm not sure if you all know this, they had to stop their observing run because of the virus and people could not be on site. So O3D, the current observing run, actually ended a month or so earlier than what it was supposed to be. The event so far and what, you know, the field, where the field is going is actually pretty incredible. And if you see this, you know, steep increase on the number of events. During the first two observing run, there were about 10 black hole binaries detected, one binary neutron star, the famous, you know, multi-messenger event. Another binary neutron star from the third observing run has already been published, and independent searches found other triggers that might or might not be real, depending on, you know, the assumption that goes into the analysis, or so. Let's say they are lower significance triggers. The current runs is providing many surprises so far. We're talking about 50 or so candidates, including several, you know, binary neutron star candidates, a few guys that could even be, you know, black hole neutron stars, so mergers of a black hole and a neutron star. Some candidates which are, we don't know, something between a neutron star and a black hole. There was even a burst trigger, so something unmodeled, which does not look like a binary, which so far is unclear what this is. For the, you know, in relation to what I'm gonna say, it's useful to point out that one of these black hole candidates is actually very massive, or I mean, the masses are not released publicly, but it's very far, about more than 5 gigaparsecs away. And because LIGO is more sensitive to high mass events, in order to see something so far, it has to be massive. We're talking about 100 maybe or so, or solar masses. All right, so, and the best is to come. So in the plot that I have here, this is a collection from some of the predictions that we put together, a year ago or so, merging some stellar simulations. And we are talking about a growing catalog of gravitation wave events that is going to go into the, well, thousands, pretty soon, in a few years or so, and millions by the end of a few decades or so. So the field is really entering a large statistics regime, and yeah, where really the best is yet to come, which is what we're kind of seeing already with these events that are going to be announced soon. So one key feature of black hole masses is the so-called, the presence of the so-called mass gaps. So in this plot here, I have, I'm looking at the right panel. So I have the mass of the zero-age main sequence, so the typical mass of each star, forms or so, and the mass of the compact object on the y-axis. And as you see, there are regions which appear to be forbidden. So these two gray areas here appear to be forbidden in a sense that, masses, stars do not tend to form and populate, the black hole distribution in those locations. So there are two gaps, a so-called lower mass gaps around 3 solar masses or so between neutron stars and black holes, which we don't know or don't understand even if it's there at all. And what I'll be really talking about during this talk is the so-called upper mass gap at about 50 to 100 or so solar masses, where again, we don't understand, or no, we do understand, but it's unclear if stars can populate that gap or not. Why we think there's a gap? That's because of the so-called peri-instability supernova. So the process goes as follows. So in this plot here, taken by this Farmer paper, I have the CO here is carbon oxygen, so carbon oxygen mass on the x-axis, and the black hole mass on the y-axis. So as you increase the mass of the core at low masses, so say 30 or so solar masses, the mass of the black hole increases. Right? The more mass, the end product will be larger. But then at some point, the spectrum is capped at about 50-ish or so solar masses. The reason is electron-positron production. So the more you increase the mass, you reach temperatures which naturally create pairs of electron, and in which a photon decays into electron and a positron pair, which means that the radiation pressure in the core drops. If the radiation pressure drops, the core contracts, the temperature goes up. We have a ball of oxygen that is, heating up and might become explosive. So if the mass of the core is too high, you ignite explosive oxygen burning, meaning that the mass of the final object is less massive than what it could have been, because most of the carbon and oxygen has been burned away. There are different regions here. So at the far end, so more than like 60 or so solar masses, these are pure pair instabilities, meaning that the entire star is gone and there's no remnant at the end. In the middle, say around 40 to 50 or so carbon oxygen mass, what you have are a series of pulsations. So not all of the carbon and oxygen, burn at the same time, but some of them does. This decreases pressure, meaning that the electron-positron production stops. The core can, start contracting again, eventually reigniting the oxygen or so. So you have a series of pulsational pair instabilities that eventually dissipates some of the mass, but not all of it, leaving behind the black hole, which has a maximum mass of about 50 or 45 or so solar masses, something like this. So the key from our supernova friends is that black holes with masses larger than, say, 50 or so solar masses are believed to be forbidden. Now, there are papers around showing that this limit is actually very solid, until, of course, somebody finds a shortcut or, a caveat to show why this thing can be evaded. There's even a recent optical observation, this LB1 guy, which is supposed to have a mass of 70 solar masses, which is unclear. The point is that whether you place it to 50, 60, or 70 or so solar masses, at some point, stars are bound to fail. At some point, stars cannot form a black hole which is too massive, certainly cannot do a 100 solar mass black hole. So the point that I want to raise here is, can we bypass stars and instead use black holes to populate these regions of the mass spectrum? So one more information about the LIGO events and how the gravitational wave detection works. These regions of the parameter space at about 100 solar masses or so is actually within our reach. So in the panel in the top right, I have the horizon redshift of LIGO for a given masses. So for each point in the mass 1, mass 2 plane, so there's the two masses of the black holes, assuming M1 is greater than M2, that's why only the lower part of the plot is actually colored. The contour lines, and as you see the values there, shows the horizon redshift. So that's the largest redshift at which things are detectable. It changes as long as the mass is below 100 or so solar masses. So their region at 50 solar masses is actually a hotspot where we should see many events if they are there. And actually, the fact that we don't see these events so far, at least in the first and second observing ground, already point to the fact that these events probably are not likely, or they're not very many or so. The figure below is a result from the population fit developed by the LIGO collaboration. We show evidence of a cutoff of an upper mass cutoff at about 50 solar masses, where these events cease to be there. Now, all the point now becomes, if there's an outlier out there, so if we do see out of a population of many, let me call them low mass events, a single outlier at 100 solar masses, what is this going to teach us about the population of black holes in the universe? And all this, line of reasoning should be placed into the so-called field cluster debate. And what I want to say here is that there are mainly two ways of forming black holes binaries, at least, the two most dominant channels. On the left, you have two stars that, have been together for all their lives. That's a binary star. One of the star collapses, forms a black hole. The other star collapses, then forms a black hole, and you're left with a black hole binary. So these guys have been together for all their lives. Or you can have two stars that were not part of the same binary. They separately collapse and form black holes. And once they're already black holes, they meet and form, binaries or so that then will merge and be detectable by LIGO. Then, of course, for this scenario on the right, you need some form of dense stellar environment, like a stellar cluster or so, to assemble dynamically these black holes that then will eventually merge. So we want to bypass the upper mass gap, and we kind of want to do it with clusters. The idea here is multiple generations of black holes. So what if instead of, suppose look at the on the right of my slides. So suppose you have stars up here, they collapse, form first generation black holes, that they respect the pair instability mass gap, because that's how cores behave, or we think it behaves. So you could have two first generation black holes that form a binary, and that's what you see. Or all on the right, you could have first generation black holes that merge together. Now these second generation black holes now can be bigger than 50 solar masses, right? You got 50 plus 50, that's 100 or so. Two of these guys meet and form a second generation event, which at that point is a merging binary in LIGO that can evade the pair instability mass gap. So the idea here is, can we fill the upper mass gap with the repeated mergers in clusters? So two more key ingredients to these pictures. One of them is the spins, and there's a so-called magic number here. Well, so-called, I called it. The physical mechanism here is the orbital hang-up effect. So the upshot is that more or less whatever you do when you merge two black holes, the final black hole will have a spin of about 0.7 in dimensional units. So when extreme Kerr is 1 and Schwarzschild is 0. The reason here is the orbital hang-up. So in this blue square picture here, frame that I have, so you can have two black holes which are aligned with the orbital angular momentum of the binary. So L is aligned with S1 and it's aligned with S2. At merger, these three angular momentum get converted into the spin of the final black hole. But in this case, they are aligned, so you have to do L plus S1 plus S2. Although the binaries, if spins are aligned, will inspiral for a little bit longer. So the black holes are closer, so that the angular momentum is a bit lower. So you do L plus S1 plus S2, but L is a bit shorter. If on the other hand, the spins are anti-aligned, the binaries plunges from afar. So the orbital angular momentum when merger is a bit larger, but you have to do L minus S1 minus S2. So these two effects counterbalance each other, and the end product is that the final spin has a very characteristic and peak distribution. So in these plots on the right, I have a specific realization of this idea. So I start from spins, so for the primary black hole in the top and the secondary black hole at the bottom, which are flat. Their distribution is flat from 0 to 1 for the first generation blue line. And already by the time of the second generation, the distributions are highly peaked at the specific value of 0.7 or 0.68 or so. So these multiple generations of black holes should have a very specific signal, which is they should be highly spinning or moderately highly spinning. All right, so next ingredient are black hole, so small kicks. So black hole kicks are due to the asymmetric emissions of gravitational waves and mergers. So gravitational waves dissipate not only energy and angular momentum, that's what's causing the shrinking of the binary, but also linear momentum. So a dissipation of linear momentum means that the center of mass of the binary recoils in the opposite direction. So this opens for the scenario that you have two black holes that merge with each other, and the final guy receives a recoil or a kick, that could potentially kick him out of the. So for non-spinning black holes, generic kicks are of the order of hundreds of kilometers per second. The real fun starts when you have spins when you add spins into the business, and there could be super kicks, the so-called super kicks of about thousands of kilometers per second, which is enough of like ejecting black holes out of the most massive galaxies in the universe. Moreover, if the binary is eccentric, these kicks are even enhanced, and we recently found that the effect is as large as 50%. So I have an animation here. I hope you see it through Zoom as well. Which what I'm doing are integrating the equation of motion to find the motion of the center of mass of the binary. And as you see, there's very little going on at the beginning, and then right at merger, the merger happens at the blue point. The binary, the final black hole shoots out in some direction. In this case, a velocity of 1,000 or so kilometers per second. So it's much like a rocket. You're shooting gravitational waves in one direction, and your rocket goes up. All right. So let me go to the core of this talk now. So what if, just assuming, LIGO sees an event which is in the upper mass gap, and I want to do this with multiple generations of black holes, mostly because I don't know what else I should be doing. This looks like a well-motivated scenario. So the question I want to ask here is what kind of astrophysics we can infer. So I'm not going into n-body or sophisticated cluster modeling. So for me, in this talk, a cluster, what I'm going to call a cluster, is just a thing. So a collection of n black holes which has an escape speed v, and I want to test the impact of these escape speed on the population of events that I can produce. So I will be distributing masses according to some initial mass function. Spins are distributed uniformly from 0 to some maximum value, and this chi max is going to be a crucial parameter of this problem. And once I have my collection of black holes, I pair them. So I pick one, and then I select its companion based on the observed population. So this is calibrated on current observation. So I'm picking the LIGO fit and the exponents that they measure this. All right. So what I'm going to do is kicking the black holes out of the cluster one at a time. So I have my collection of black holes on the left. Then on the top, I select two black holes, pair them according to my probability, their gravitational wave emission, and record, and I keep track of all the black holes and all the events that LIGO should be seen. These gravitational wave will be filtered by LIGO detectability, so taking into account selection effects, if you will. These two black holes will merge into a bigger black hole, and at that point, I have two options. So the kick that this black hole receives is larger than the escape speed of the cluster, which is a free parameter for me, I'll just take it out of my sample. Otherwise, if it's smaller, I'll put it back. And then I iterate until there's only one black hole in the cluster. All right, so these two plots show some of the results. On the left, what I'm showing is the sample of individual masses, so either the primary or the secondary mass of the binaries, filtered by LIGO detectability. So what I have on the y-axis is the probability the LIGO will detect an event in that bin count. So I'm basically weighting my histograms by using information on the LIGO detectors. So what you see here is that there's a sharp cutoff at 45 solar masses. That's my injected first generation black hole. So I'm assuming that stars, the peri-instability supernova works and stars respect these mass gap. So you see there's a smaller population of black holes at larger masses, up to 100 or so, which is made of higher generation black holes. So these black holes that repeatedly merge inside the cluster. Population, as you expect, is higher if the escape speed of the cluster is higher. So the red line has more events in the mass gap than, say, the blue line or the orange line. On the right, I'm dividing my sample in generations. So the blue lines, the blue histogram is like considering only the first generation of black holes, while the orange, red, and green histograms consider higher generations. As you see, only the high generation can fill the upper mass gap, and we have events which merge many times, 3-4 times or so inside the cluster. All right. So crucially, I was saying one of the key parameters is the escape speed of the cluster. And the reason is that kicks will eject black holes unless the escape speed is high enough. So in this plot on the right, what I have is for 3 different values of the maximum spins, I have the distribution of kicks that black holes detected by LIGO receive. And as you see, kicks appear to be discontinuous at small spins. So for the blue line, you see, look at solid blue. That's a cluster with the escape speed of 10 kilometers per second, where all black holes are born slowly rotating, actually not rotating at all. And as you see, there are 2 peaks here, one at about 10-ish or so kilometers per second, and another one at about 1,000 or something. This first peak disappears as long as the spins is not small, not fine-tunedly small. And that's because, so what this plot is showing is that the natural kicks that black holes will receive is of the order of hundreds or so kilometers per second. And there's little fine-tuning that you can do to get around this and avoid this fact. This plot on the right shows that despite this being a simple model, I'm in a regime where my physics is converged, in a sense that if I change the number of black holes I start with, results are solid. So the results of these we have in this paper is contained in these plots here. So here I have for two different prescriptions for the pairing. So the way I put black holes together. On the right, I have selective pairing, and on the left, I have selective pairing, meaning that I use the LIGO population to actually decide which companion is more likely for each black hole. And on the right, as a, to bracket the uncertainties, I have random pairing, where I randomly select a black hole from a cluster and pair it with another one. The left panel is more physically motivated, if you want. So on the x-axis in this plot, there's the escape speed of the clusters, and on the y-axis, there's P gap, which is the probability that LIGO will detect an event in the mass gap. And as you see here in the insets, if you want a probability of a few percent or so, the escape speed needs to be larger than about 50 or so kilometers per second. And this is the driver here, is that kicks are easily above 50 kilometers per second, and they're easily in the hundreds. The notable exception is selective pairing and very small spins. So in this case, all black holes are very close to being equal mass. The spins are very close to being zero. And where you have an equal mass black holes with 0 spins, the system is completely symmetric, and the kick is 0 by symmetry. But this is an extreme case if you want. So note that these predictions are conservative. Crucially, we are neglecting eccentricity, and we know the mergers in clusters are believed to be eccentric, some of them very highly eccentric. And we recently estimated that eccentricity can enhance the large escapes by up to 25%. So the key, the take-home message here is that an escape speed of about 50 kilometers per second is necessary to populate the mass gap, and there's little, room to play with. All right. So why this is relevant? Well, 50 kilometers per second in astrophysical terms is more than most globular clusters, which are believed to be, one of the crucial and most important environment to host black holes. So in this plot on the right, I have for different, systems, from globulars, the triangles at the bottom, to large ellipticals, the squares at the top, their typical escape speed. And globulars, maybe you can get up to 100 or so, but most globulars, we're talking about the escape speed between 10 and 50 or so kilometers per second. So this raises an interesting point, which is, well, what can do that, right? So if you see a black hole of 100 solar masses, individual stars cannot do it, individual binaries, because of the pair instability. Globulars, maybe a few, but probably cannot do it because of their low speed. Same things for young star clusters or so. The point here that I want to raise is that we need something more, something denser, something that has a larger escape speed that can retain multiple generations of black holes.
So, Davide?
Yep.
Sorry, I kind of wanted to jump in here. I disagree with the assertion that the 50 kilometers a second is typical for globular clusters over their lifetime. It's true that that's the case for most globular clusters today, after 12 to 13 billion years of evolution, but we're pretty sure that they've all lost at least half of their mass overall from their birth times, and that they've expanded in terms of radius by factors of at least a few. And that can drive the escape speed down for instance, 47 Tuc today, one of the more massive clusters, has a 50 kilometer a second escape speed. If you follow it back and account for that mass loss and concentration, its birth escape speed was probably 100 or 150 kilometers a second. And those massive clusters are the ones that are producing most of the binary black holes.
But they merge outside, right? Or they remain inside, in situ to merge again?
It's roughly a 50-50 split.
Okay.
And in fact, as you dial the mass up, you get a higher and higher fraction of mergers that occur inside the cluster as opposed to being ejected.
Okay. Well, thanks for the remark. So, okay. So maybe I was too. Maybe my remark was too strong. So maybe a few globular clusters can do it far away. So back in time, and if the mergers happening in situ and things. The key point, though, that I want to raise is that we should be looking for. The higher the escape speed of the environment, the easier it is, I believe, to explain these kind of events. So what I have done here are, other ideas of what you could think about doing or so to naturally explain high mass events. So while nuclear star clusters are a natural explanation, disk-assisted migration in accretion disk, and I have slides on this because I think it's particularly interesting. Stellar triples, if you manage to avoid disrupting the binaries, maybe can do it. You could also populate the mass gap fictitiously. Maybe you have a lensed event, so an event that is not really that massive, but it looks massive because it's been lensed or so.
David, a question?
Yeah. Yes.
So one thing that you didn't mention is if you want to achieve a high escape speed and you just have the mass associated with your black holes, then you need the cluster to be extremely compact, and that may make it unstable dynamically because, if it's a small number of objects that have a very high, very small size, it may evaporate. However, if you have a central black hole in the system that dominates gravity, and that's what gives the high escape speed, the situation is quite different. So perhaps one thing to ask is the stability of that system.
Yeah, thanks. That's great. That's a great comment. And actually, this goes into the nuclear star cluster idea that I have here on the slide. The idea being that there, the escape speed is driven by the supermassive black holes at the center, not really the collection of objects that then will eventually merge. And so, so yeah, maybe, I don't know, maybe an event like this could be, I don't know, used to constrain the presence of an intermediate mass black holes in a cluster. I don't know, maybe I'm going too far. So what I want to say is that, I mean, these events should really, you know, be puzzling to us and, you know, prompt us to, you know, think carefully about and creatively about what this could be. You know, done. This is my last slide. I have these slides on a plausible, in my opinion at least, scenario that I've not worked on, you know, personally, but I think is extremely promising, and it's getting lots of traction recently. And I want to, you know, touch base on this. So the idea here is forming black hole binaries embedded in disks in active galactic nuclei. So the strategy here is that you have a supermassive black holes, an accretion disk, you know, around it, and there are believed to be so-called migration traps. So if you put a perturber in the disk, say a stellar mass black hole, that's supposed to migrate into the disk because of viscous interaction. So this process is analogous to planetary migration. Like people that need to explain hot Jupiters close to their stars, they form the hot Jupiters far away, and then they migrate them inwards through the disk. There are believed to be locations in the disk which act as migration traps. So where the migration goes in one direction outside, so inwards from outside and outwards from inside, that could act as a natural place to bring these black holes together. So this could be a single scenario that, you know, in one shot will give you, well, one, a large escape speed to avoid losing black holes out of, you know, gravitational kicks. That's because the escape speed is driven by the big black holes in the center. Two, a natural way to assemble multiple generations of black holes. Because once the black hole is kicked and back into the system, could be brought back to the same migration trap, so merge again. So this could be, in my opinion at least, one of the most promising way to actually put the black holes together, retain them, and have them merging again, so filling the upper mass gap. There's even a paper out showing that the most massive event in the current observational set could be an outlier. So could be an outlier of the given population, and well, according to these people models, is matched by their AGN scenarios. Now, in the plots that I have down below, some predictions from the same paper, which are again interesting. So, you know, in the mass spectrum, what they predict happen is that, which actually, you know, typical of these multiple generation ideas, is not really an AGN scenario. This is really because of your merging many black holes. Again, you have the various generations that create these like staircase, you know, features or so. And actually, so people in the LIGO collaboration are actually developing a pipeline to look for staircase in the mass spectrum, to hunt for multiple generations of black holes. The spin distribution, and here I have the so-called effective spin, which is the LIGO observable, might have this very prominent peak at about, you know, 0.4, 0.5 or so, which is again is due to that magic spin number or so that I hinted at above. And crucially, this is the absolute value of the effective spin. So you should imagine another distribution and negative values, you know, mirror from this one. So a bimodal distribution that could be a smoking gun signature of these kind of you know, scenarios. So to conclude, I think that the prediction here, besides all these AGM business and stuff, is kind of solid. So a population high mass and high-ish or so spins event, which are not kicked out from their environment, so filling the upper mass gap. And well, this was, you know, all from me. I hope I convinced you that, you know, gravitation wave is still an exciting field to work in. The field is booming. We are entering the large statistics regime. We're talking about, you know, 50 events today, hundreds of events in a few years, 1 million in a decade or so. High mass events could be explained, or one of the most natural explanation is the occurrence of multiple generations of black hole mergers. And I hinted that the escape speed of the environment plays a crucial role for the very simple reason that gravitational wave kicks or merger kicks needs to be smaller than the typical escape speed of the environment if you want to retain the black holes and have them there to merge again. And then I concluded with some, you know, remarks or questions or speculations on what the right environment for these systems could be. And that's all. Thanks for having me here. Hope it was not too terrible over Zoom.
Question? Can we ask you questions now?
Sure.
So if there is, so you're suggesting perhaps there is a central supermassive black hole that is allowing the high escape speed, and perhaps there is a migration trap. That's where the more massive black holes are made. The question I have is, if you have a supermassive black hole, then it will drive quasi-Lidov oscillations of the binaries, right? So you might expect eccentric mergers. Do we have any constraints on those? Or would you expect that to be a generic signature of events like that? Because of the existence of a third body that is very massive in the neighborhood.
So I'm not the a better people that are more expert than me in the audience. So my understanding is that yes, eccentric mergers, and some of them are predicted. Binaries do circularize in GR, so that's that goes in the opposite direction. In terms of constraints, so far, there's also a problem of the templates that I use to look for gravitational wave, which so far are circular. There are constraints on the largest values on the eccentricity on the detected event, and it's all very small, like 10 to the minus 4 or 5 or something like this. There are other strategies like so for a highly eccentric event, the signal in LIGO is much like a series of peaks of bursts of waves, more than a full binary signal or so. So people are looking this with different techniques, and there was actually a burst trigger in the O3 data. So who knows? Maybe that's an eccentric event. I don't know.
Okay, thank you. So anyone that wants to ask a question, please raise your hand. Again, click on the participants, and then at the bottom left, you can raise your hand, and we will know that you're interested in asking a question. Okay, we have two hands, Carl and then Flor.
Hey, Davide, I enjoyed the talk.
Hi,
my other question has to do with the assumptions on the spins themselves. At this point, so in order to get those high escape speeds, you do need some amount of first generation spin, right? Because otherwise the mass ratio kick is it maxes out at 180 or 175 kilometers a second, but it doesn't. But because you have a preference in clusters for producing equal mass binaries, you mostly eliminate it. I wonder what happens if you put in some of the models from Jim Fuller and his group on sort of the survival, on sort of how much angular momentum you can actually transport into the black hole, because they've been predicting very low spins for black holes from massive stars, something around 0.01 or 0.0, or I think maxing out at 0.1. And so wouldn't that sort of really improve the retention even in low escape speed clusters?
Yeah, so if you look at this plot here, so what I have here are cases. So look at the left panel, which is selective, means it's really basically all equal mass because the pairing power spectrum is very steep. So what I have here, as you see, the Z case is actually an outlier. So all on the left of the plot. And indeed, these are all the zero spin events. The first generation zero spin event, they received very little kick. Although I have to say that the kicks are very sensitive to the spin. So even moderate spin, I don't have a line at 0.1, but it's going to be very close to the 0.2 line. So it's a discontinuous. Kicks are discontinuous at zero spins. That's what I want to say. And that's because you have a symmetry built in that, zero spin equal mass, that the kick is like zero by construct. So yeah, we could certainly, put together Jim's idea, and you have a paper on this where, you do find some of the events in clusters. The point of this study was really to stress the role of the escape speed.
Yeah. Just so I understand, in this plot, P gap is just the number of detections you would expect in the gap. So out of 10 detections, you would, okay. Thanks.
Yes, that's correct. So it's weighted by LIGO detectability. So it's the probability of observing an event in the gap.
Okay, Flor has a question.
Yeah, so thanks for your presentation. So it seems that you showed that like with, at least with already a different formation scenarios, so through AGN disk or global clusters or nuclear clusters, you can form these like kind of similar events, and that actually within a model, you have much more variation than maybe between the models. So is there any way that if all of them kind of produce these multiple generation mergers to like distinguish between the scenarios from LIGO, or not really?
Well, I don't know. If you have a merge in a disk, you might have some optical, not optical, but some electromagnetic counterparts. But things, you know, you got gas around, or so. That's an option. I'm not sure how this is. I'm not sure. I haven't worked or so on this. I think this boils down to actually, you know, try and constrain the generation. I mean, it's a difficult thing. Like what I think it's solid is that however you do it, if you merge repeated black holes, you're gonna have high mass and spins of 0.7, right? So you do see an event like this, and that's a solid prediction. That's just, you know, how, you know, angular momentum dissipation also in GR. Then yeah, then how you do it then boils down to the actual distribution, which can actually predict the rates and things. So it becomes more complicated, but some trends are solid, I think.
One thing to keep in mind about electromagnetic counterparts is that you really need the luminosity of the source to be very super Eddington for it to be visible at cosmological distances. Yes. That's why we see gamma ray bursts, but we can't see, you know, an X-ray binary from a gigaparsec away. Yes. So if these black holes just accrete gas from the disk around the supermassive black hole, they would do it at sub-Eddington levels, and it will not be visible easily. Yeah, you need really a core of a star to collapse on them in order for them to shine brightly enough.
Yeah. And moreover, I mean, high mass events are going to be going to be rarer and far away. So we see them very far away, meaning that catching counterparts is, you know, much harder because they're going to be very far. So right. Probably it's just.
But we can still bear hope on low mass second generation mergers that's close by, right?
Correct. So on the low mass second generation guys, so one other ideas is that, so if you do see a high mass guy and you know that, say, I don't know, a globular cluster or whatever can populate the mass gap with a fraction of about, I don't know, 1%, or I'm just making it up. If you do see one, it means that 99 of the other events comes from the same channel. So you can use one event out there to constrain, you know, to say something on the bulk of the population. Does it make sense what I'm saying?
Yes.
So so if you predict the efficiency with which a given environment can, you know, populate the gap, one event then gives a constraint on the much larger bulk of the population.
And we possibly will see a bimodal distribution for low mass black hole.
Yeah, maybe then you could possibly correlate with mass outliers. That's the strategy, I think.
Any other questions? Well, Davide, that was an excellent talk, very exciting and interesting, and we wish you most success in finding more of these massive systems. That will be a very interesting frontier for the future.
Thanks for inviting me. I hope I'll be able to come for real at some point.
Yeah, we look forward to seeing you. Thank you, everyone, and see you next week.
Bye-bye. Thank you.